Swayam Prabha. Digital India. Educated India.
Today is the fifth lecture in this lecture series on jet aircraft propulsion. In the last class, we talked about basic turbojet engines and we talked about a variant which includes a reheat or afterburning added to basic turbojet engine. So, we were essentially talking about turbojet engines with or without afterburning. Today, we will talk some other variants of jet engines meant essentially for aircraft flying, and these are the variants which are often categorized in the form of turbofan engines. And there are so many variants of turbofan engines, and we will take a look at as many of them as possible today. We will also have a look at these variants with reference to the performance parameters that we have talked about in the earlier lecture. Today, let us take a look at some of these variants which are used in most of the modern aircraft today, especially the transport aircraft, and they provide the bulk of the service with reference to aircraft flying all over the world. The various kinds of jet engines that we will be looking at today essentially cater to more efficient flying. They also cater to bigger engines, which often are used in big aircraft, which carry very large number of passengers or cargo. And as a result of it, it is necessary that they are very efficient and very useful and very reliable in terms of flight applications. Let us quickly take a look at the list which we had a look at once before, all kinds of jet engines. We had talked about that there are so many kinds of jet engines, and the same list today we will look at very quickly. You see, on the left side there are three varieties, the turbojet and the afterburning and non-afterburning, which we have talked about in the last class. So, we will not talk about those variants anymore today. We will talk about a little on the turboprop, turboshaft, which are very broadly can also be categorized as jet engines, in the sense that they use the basic engine which is same as a jet engine, that is the gas turbine engine, and we will be talking about the turbofan engines and a modern variant of turbofan or some kind of a cross between turbofan and turboprop, that is the prop fan, which has two variants, one is unducted, another is ducted, and we will take a look at this prop fan also today to understand how it works. So, let us first start with the variant that is connected to turboprop and turboshaft, but let us take a look at all the turbofan variations that we will be taking a look at today. Turbofans come in various shapes, sizes, and of course, various thrust categories. Now, on the left hand side again we will see a few of them which are mixed flow and unmixed flow and non afterburning and afterburning. Some of these appear on the right side also. These are the ones which we talked a little about in the last class, essentially categorizing them as jet engines, and we felt that there is very little difference between these low bypass turbofans and basic jet engines, and hence we talked about them in terms of how they function, how they work, and how to assess their performance by using the fundamental performance parameters. So, we will not be talking about those ones, but we will be talking about the other ones which are shown in this list here today. We will be talking about the forward fan, we will be talking about the aft fan, and of course, we will be talking about the high bypass ratio fans, which come in single spool, 2 spool, 3 spool, and then of course, we will have a look at the geared fan, which is a special variety of large turbofan engines. So, these are the ones which we will be looking at today in some detail and try to look at their differences and how they function and what their mechanical details are and exactly how they compare with each other. Okay, so, let us start off with what can be called a basic turboprop engine. Now, a typical turboprop engine essentially is run by a basic jet engine. Now, basic jet engine, what it does is it has the capacity now to produce more power than is required to run the compressor. Now, this turbine, which is now capable of producing so much of power, is now, as you can see in this particular diagram, has a very large number of turbines in the second group, or what can be also called the low pressure turbine group. And in this we can see there are 4 turbines, which means the aggregate amount of power that this group produces is so much more that it can easily run a big propeller. And this combination of a basic turbo engine with a propeller is simply called turboprop engine. Since this variety of engine also produces a hot jet and produces a certain amount of jet thrust, some people also call it a prop jet engine. So, it is a combination of propeller and jet engine. Propeller by design produces the bulk of the thrust. So, the flow goes through the propeller in a normal cold air flow, and that produces the bulk of the thrust, quite often of the order of 80 to 85% of the thrust, and the balance 50 to 20% of the thrust is produced by straight jet that a typical jet engine produces. Now, this particular kind of turboprop engine can indeed come in single spool. The one that is shown here is actually 2 spool. It has 2 shafts, one the concentric shaft, as you can see, which comes from the low pressure turbine group, all the way runs what is also can be called a booster compressor or a LP compressor, and then through a gearbox runs the big propeller. Gearbox is an absolute necessary element in a turboprop engine, because the propellers never run at the same speed as turbines. Turbines run at a much higher speed or RPM, and it is necessary to reduce the RPM substantially before you run the propeller. However, just before the gearbox, on the same shaft you may have this LP compressor or booster compressor, which simply boosts the air which is coming inside the basic engine or core engine and produces sufficient amount of pressurization, which is then fed into the main compressor to do the compression before it is fed into the combustion chamber. Now, this main compressor is run by 1 HP turbine, which is often sufficient to produce sufficient power to run a whole group of compressors. Now, that is run by the outer spool over here, and hence this is a 2 spool engine. A smaller version of turboprop engine can indeed be a single spool turboprop engine, which means it comes through one single spool, and then you have one group of turbine which runs one group of compressors, and then through the gearbox again runs the propeller. So, propeller has to have a gearbox before the power is sent to the propeller, because as I said, the propeller runs at a much lower RPM, normally of the order of 1000 to 1500 RPM, whereas the turbine compressor spool often runs at many thousands of RPM, quite often of the order of 8 to 10,000 RPM. So, this is a typical turboprop engine, or as some people call it, a prop jet engine. Let us look at how the turboprop engine performances can be estimated. As I mentioned, 15 to 20% of the total thrust can be created by the jet engine. So, hence you have two components of thrust making here, one by the propeller, one by simple jet thrust. The total thrust can be written down, let us say, as F t, and then the thrust horsepower can be measured in terms of F t into V, V being the velocity of the aircraft flight. And then this thrust power has two components. One is in terms of the power supplied to the propeller, which is the brake horsepower coming from the engine through that spool through the gearbox and supplied to the propeller, and eta p of course, is the propeller efficiency. And the second term of course, is the thrust power created by that 15-20% of the straight jet thrust. So, two of them together make up the total power consumption of this engine, and quite often they are expressed in terms of power rather than in thrust. One could do it the other way around, but this is basically a power driven machine, and hence most people would like to categorize turboprop performance in terms of horsepower or kilowatts rather than directly in terms of thrust in kilonewtons. Alternately, quite often this can be shown in terms of what is known as equivalent shaft horsepower, and this is given in terms of bhp as supplied by the main shaft to the propeller, and the jet thrust that is being created converted to power. Now, this is converted with a small propulsive efficiency of the jet thrust, and so we have the second term, which is basically a thrust power converted to power, which is then added up to the shaft power, and the two of them together makes up for what is also known as equivalent shaft horsepower, or ESHP. Now, this ESHP is what is supplied, let us say, to the shaft for creation of power, and hence that power, thrust horsepower, as we categorized earlier, is directly a result of ESHP into the eta p, which is the propeller efficiency, and hence we can also get a THP as a measure of power supply of the whole engine from ESHP. The total equivalent thrust, as I mentioned, can also be then written down as F t equivalent equal to THP by simply V. V of course, is the aircraft velocity. So, as a result of which it is possible to write down equivalent total thrust in terms of the total horsepower that is being consumed divided by the aircraft velocity. The specific fuel consumption of this kind of engine is often given in terms of kilograms per hour per kilowatts, which is what the power consumption is normally of THP or ESHP, and the definition remains same as before, that is the fuel consumed m dot f divided by THP, and that is expressed in terms of kilograms per hour per kilowatt. SFC can also be expressed in terms of m dot f divided by ESHP. Actual value, as you can see, would be slightly different, and it is possible also, if you wish to, it can be expressed in terms of m dot f by F t equivalent, and in which case the units would be kilograms per hour per kilonewtons. All three possibilities exist. However, the most common and popularly used one is the first one, and that is SFC expressed in terms of per unit power, that is kilowatts, for turboprop engines, because turboprop engines are normally specified by the power consumed and not by the thrust that it produces during flight. Let us now take a look at some of the other variety of engine. Now, this kind of an engine is called a turboshaft engine. It is slightly different from turboprop engine in the sense that it also uses a basic jet engine or a basic gas turbine engine, same as turbojet engines, but it does not produce any thrust at all by the jet propulsion system. It produces all its thrust with the help of a rotor, and this is often not called a propeller, it is called a rotor. And the reason is this kind of rotor actually runs on a horizontal plane and produces thrust often mostly in the vertical plane. So, unlike a propeller which runs in the vertical plane and produces the thrust in the horizontal plane, that is in the plane of motion of the aircraft. In case of a turboshaft engine, the rotor moves in the horizontal plane and produces thrust in the vertical plane. Now, this production of thrust directly allows the craft to be lifted off the ground, and this is used for helicopters. This is the kind of engine that is used for helicopters for direct lift off from the ground, which requires that the thrust produces to begin with balances the weight of the entire craft, and that is the first requirement for the lift off. And once it is lifted off the ground, the shaft of the rotor can slightly tilt forward, and then it produces certain amount of forward thrust with which the helicopter flies forward. As you can well imagine, it is only a small component of the thrust that is being produced by the rotating rotor, and as a result of which the amount of thrust that is available for forward flight is often not very high, and hence the helicopters often do not fly at very high speed, they fly at rather low speed. They also normally do not fly at very high altitude, they fly normally at somewhat lower altitudes, almost well within the eyesight. And all this time during the flight, remember, the helicopters do not normally have wings to support the craft during its flight by creating lift. So, there is no lift creating surface or body attached to the craft like wing, and hence the rotor has to continuously support the body of the helicopter during its flight, the weight of the helicopter. So, it is a continuous weight balancing thrust that the rotor has to create during its entire operation and during entire flight. So, only a small part of that thrust is available for forward flight. So, this is the kind of engine that is simply called turboshaft engine, because it produces a shaft power and makes a rotor rotate in the horizontal plane, and it is simply called a turboshaft engine. So, let us take a look at this turboshaft engine, which is shown in the diagrams over here. Now, as you can see here on the left hand side, this shaft is coming out of the engine, and at the end of this shaft you would again have a gearbox, and you would have a big rotor which will be powered by this engine. Now, this is a straightforward turbo engine or a gas turbine engine, and this is a big turboshaft engine, which is a 2 spool engine. The inner spool is what is coming out to run the rotor. The outer spool runs the basic compressor turbine loop, creating the power or the power generating system. On the right hand side, we have a slightly smaller engine, a medium sized turboshaft engine, in which what has been deployed is a combination of axial flow compressor and a centrifugal compressor. And this combination is very popular in turboshaft engine, because it provides a very compact engine producing sufficient power through the shaft to run the rotor. So, here also this rotor shaft would be coming out over here, and there of course, would have to be gearbox to run the rotor. The rotors also typically run at very low speed, like the propellers, quite often even lower speeds, less than even maybe 1000 rpm, and these rotor sizes are much bigger than that of propellers. The rotors can be as big as 8 to 10 meters in diameter, and as a result their rpm would have to be somewhat restricted for various structural and aerodynamic reasons connected with the rotor motion. Now, this is one kind of turboshaft engine which I mentioned is very popular, where you have a combination of centrifugal compressor and a axial compressor or a set of axial compressors, which of course are run by a single shaft of a set of turbines. In between, of course, you have the combustion chamber. On the other hand, there are other varieties which we can take a look at. Now, look at this engine, which is a cutout of a typical turboshaft engine. Now, what you see here is you have a combination of an axial flow compressor and a centrifugal compressor. As you can see here, the centrifugal compressor is quite large and produces substantial amount of compression. Then it delivers the air into this combustion chamber, which is a kind of a reverse flow combustion chamber, in the sense the flow goes into the combustion chamber and kind of backtracks back in the actual direction. So, actually it sort of comes back through the combustion chamber and then gets delivered onto the turbine. So, this combustion chamber is something like a wrap around combustion chamber around the entire engine. So, it is a combustion chamber that wraps itself around the entire engine, inside which you have the turbine, and as a result of which this is typically a reverse flow combustion chamber, which, as I mentioned, then delivers the hot gas into this turbine. Now, this is the compressor turbine. Now, this compressor turbine runs this compressor combination of axial and centrifugal flow. So, this basically supplies power through the shaft to the compressors, the two compressors together, and then it delivers the flow through this ducting system onto this bigger turbine, which is the power turbine. This power turbine then runs another shaft inside, which comes through, and then it runs this gearbox. Now, you can see the speed reducing gearbox over here. So, this inner shaft, it comes through the outer shaft from here, and then through this gear meshing system reduces the speed substantially, because as I mentioned, the turbine speeds are likely to be of the order of 8 to 10,000 rpm, sometimes even higher. A typical turboshaft engine can have, a compact engine like this could have speeds of the order of 30 to 40,000 rpm. That is the kind of speed at which many of the turboshaft engines could actually be running, and as a result of which the power generation is of very high order. However, the rotor cannot possibly run at anywhere near that speed. So, you have a huge reduction that needs to be done, and you have a almost something like a gear train through which the reduction needs to be done in an efficient manner, and this reduction could be of the order of 1:100 or something, and as a result of which you can see a huge big gearbox. Now, gearbox is a heavy element, and hence it adds substantially to the weight of the whole engine or the whole engine system, and as a result of which a typical turbo shaft is likely to be rather heavy. And that is also another very good reason why the engine designers, the turbo shaft engine designers, try to make the basic engine as compact and as light as possible, because it has to make way for the gearbox, which is an absolutely essential element in the turbo shaft operation. So, this is a kind of typical turbo shaft engine used in many helicopters all around the world, based on basic gas turbine engine, which is same as the various kinds of jet engines that we are discussing. This is a schematic of a turbo shaft engine, the kind of engine that we were looking at just now. It has this compressor, it has the compressor turbine, and then it has the power turbine, and this is the shaft through which the flow comes, the power comes through, and then you have this output shaft over here, which runs the rotor, and then you have the huge reducing gearbox, which reduces the rotating speed by a factor of 50 to 100. And these are the systems which you have, and this is the inlet. So, you have a sidewise inlet of air going into the basic engine, and quite often the exhaust also could be something like this sideways. As I mentioned, they do not produce any direct thrust. So, essentially they are exhaust gases, all the energy has been taken out by the turbine, and it simply goes out without any power or any residual energy left in it. It goes and mixes with the atmosphere. So, this is a simple schematic of the kind of engine we just had a look at here. So, this is the basic engine, a picture, and this is just a schematic of how it is or its layout inside that engine. This is the kind of helicopter engine that you see in a helicopter. These are the rotors that I was talking about. These rotors are very big, and they are fixed here with a very strong mechanical fixing arrangement. Some of these rotors could have variable pitch arrangement, which we may talk about separately, and these are the intakes to the engine. In this particular sketch, you can probably see there are two possible intakes, one on this side and another on the other side, and that is what we saw here. There are two intakes, one on this side, one on this side. They feed into the same engine, and you could be having similar arrangement here, that you could have one intake on this side, one intake on this side, feeding into one engine, which produces the shaft power that runs this rotor for helicopter. This is the other side of the helicopter engine. You have the exhaust coming out over here without producing any jet thrust, and this is just exhausting the used up burned gas through various ducting arrangement, so that they do not produce much interference with the main operation of the helicopter or the engine. And these are the big rotors that produce the direct thrust for liftoff of the helicopter and for the helicopter flight. So, that is how the turboshaft engines are mounted on a helicopter, and that is how they actually operate to make the helicopter fly. The performance of a turboshaft engine can be simply written down in terms of THP is equal to BHP into the propulsive efficiency of the rotor, and is expressed in terms of kilowatts. The specific fuel consumption can be written down in terms of m dot f divided by the THP, and also is expressed in terms of kgs per hour per kilowatt. So, turboshaft and turboprop engines both have power as the specification of the engine, and SFC is shown in terms of kilograms per hour per kilowatt. Shown here is a picture of a very interesting engine that has been demonstrated and even flown. It has not quite become very popular as yet, and this is simply called a tilt rotor engine, in which this is basically a turboshaft cum turbofan engine. This particular rotor is more like a fan, and this engine can actually tilt itself. It can go vertical as it is shown here, or it can become horizontal to become something like a turbofan, and this capability makes it or gives its name tilt rotor. So, whole thing can be tilted. So, while taking off like a helicopter, it can be positioned like this, and it directly produces thrust for lift off, balancing the weight of the craft. Now, once it is airborne, it can start producing power for forward thrust by simply tilting the whole engine front like this. So, from a vertically aligned engine, it can become a horizontally aligned engine, and the rotor, instead of rotating on the top, behaves more like a turbofan, and it rotates in the vertical plane, producing directly thrust. Now, this is why it is called a tilt rotor. It can tilt from vertical position to horizontal position, producing direct thrust during flight, and again during landing it can be tilted backwards to have a direct vertical landing. So, it can have a vertical takeoff, it can have a vertical landing, in between it can tilt forward to create forward motion and directly provide forward thrust for the aircraft to fly. This kind of engine has been made, they have been flown, but the mechanical arrangement of making it fly during making it tilt during flight is rather complicated and a little risky, in the sense there are some chances of failure, in which case it could be catastrophic, and because of that it is probably not become a very popular kind of engine even today, even though technologically it is a proven variety of engine. Now, let us start taking a look at various kinds of turbofans. Now, turbofans can be various kinds. One is, we could categorize them in terms of single spool or two spool or three spool. So, in terms of spools, so let us take a look at a single spool and a two spool turbofan engine. The first one that is shown on the left is a single spool turbofan. A single shaft run by a set of turbine produces sufficient power to run the compressors and the fan in front of the compressors. Now, the fan is a bigger compressor, as we have talked about before, and they are called fins simply because they are bigger and look like fans, but they produce compression as much or more than compressors, actual compressors. And after the fan you have this bypass. So, in this turbofan engine there is a certain amount of bypass, and then this is a cold flow that goes and bypasses the basic hot engine and mixes much later in the jet pipe, and the mixed flow goes out through the common nozzle. In the meantime, a certain amount of cold flow goes through the compression process, goes through the combustion chamber, through the turbine, and that is the hot gas, produces power. So, the power is produced only by the inner flow. The outer flow does not participate in the power production, it simply consumes the power. The inner flow produces the power through the turbine, and then it goes out and mixes with the cold flow in the mixing zone, and then goes out through the nozzle, a mixed flow, not very hot anymore, but the mass flow of the exhaust flow is now so much more. So, the thrust production is of a slightly higher order, and as we have seen before, this simple method of bypassing certain amount of flow and later on maybe mixing them produces certain amount of SFC benefit, a specific fuel consumption benefit, and that benefit people have been trying to harness for a long time by various versions of turbofan engine. So, various versions of turbofan engines are typically bypass engines. So, that is another way of looking at turbofan engine. So, we can look at them in terms of spools, or we can look at them in terms of bypasses, the amount of bypass they produce. When it is comparatively low bypass, bypass of the order of 1 or 2 or not more than 3, one could possibly have this kind of a mixed flow, where it later on mixes with the hot flow, and a single exhaust, mixed exhaust goes out producing thrust. The other version, which is often a two spool turbofan. Now, two spool turbofan means that the turbine works in two groups, one which is often called the high pressure turbine group, which may be a single or two turbines, and then you have the low pressure group, which is often a multi-stage turbine group, and they produce power over two shafts. Now, the HP one actually sends power through the outer shaft, which is, as you can see, a hollow shaft very much, to this group of compressors, which is also called HP compressor. Now, this HP compressor run by HP turbine creates the so called HP loop, which is wrapped itself around the combustion chamber, and this is the core engine, and quite often simply referred to as the gas generator, because this loop of compression, combustion and a turbine produces the basic gas of the gas turbine engine. So, this is simply called the gas generator. And then of course, the next group of turbine produces a lot of more power, and this power is sent through this inner shaft to this big fan. Now, this big fan is on a different shaft. So, it is called a 2-spool engine. And the other way of looking at it is this big fan now produces a very large bypass. Now, this bypass is so large that you cannot possibly have the whole engine again covered up and mixed together later on. In the sense, the bypass is far more than the inner core flow. Mind you, again the basic power produced by the low pressure multi-stage turbine is still by the inner flow only. So, the inner flow only participates in production of power, and that power is sent to the big fan, and big fan then pressurizes the cold air and sends it out as a separate jet, and this separate jet produces cold thrust. So, that is the essence of a bypass turbofan engine, a high bypass turbofan engine, where cold thrust is produced in addition to the hot thrust, and as a result of which certain amount of benefit in terms of propulsive efficiency is obtained. So, this is a 2-spool high bypass turbofan engine. The first one was a single spool, which could have been 2-spool. There is no reason why a mixed flow cannot be 2-spool. So, this could possibly be 2-spool also, but it would be a mixed flow engine of a low bypass variety, bypass of the order of 2 or less, whereas here it is bypass of the order of 3 or more, and quite often nowadays of the order of 4 or 5. Now, this is a 2-spool turbofan engine, which is a very common variety of turbofan engine used in most of the aircraft these days, which are flying around. The more modern version of turbofan engine is the 3-spool turbofan engine, which is not very popular as yet, but it is already being used by some of the engine manufacturers, such as the Rolls-Royce company, and they have been making 3-spool turbofan engine. There is a certain mechanical complexity here, because as you can see, there are 3 concentric shafts. The inner core of the shaft carries power from the outermost turbine or LP turbine through this inner shaft and carries power to the outermost compressor, which is the big fan, which is the LP fan. So, that LP spool or LP shaft essentially carries a huge amount of power from this set of LP turbines onto the LP big fan. The other 2 spools are the intermediate pressure turbine, which carries power to the intermediate set of compressors, and the HP turbine, which supplies power to the HP compressor. Of course, this inner path of the flow, which carries the air in through the intermediate compressor, through the HP compressor, into the combustion chamber, into the HP turbine, and then into the intermediate pressure turbine, is the inner flow. That is the basic gas generating flow, that is also the basic power producing flow, and then also goes out in the form of a hot jet, which produces certain amount of hot thrust. In this kind of engine, it is almost invariably it is a very high bypass engine of the order of 5 or 6, and this cold thrust that is produced is substantially higher than that of the hot thrust, and the accent is on sending a very large amount of power to this big fan, which activates or processes a very large amount of air mass, and that produces the large amount of cold thrust. So, 3-spool engine has been a proven variety that has been flying around for quite some time now, but it is still not very popular all across the world. Not every manufacturer uses 3-spool engine, and some of them prefer to still continue with 2-spool engine, and it is essentially a difference of opinion in terms of the mechanical complexity of the engine. Rolls-Royce company seems to be comfortable with this mechanical complexity, whereas some of their American counterparts are not convinced of the mechanical complexity that is required to create high bypass turbofan engines. Let us take a quick look at the thrust that is produced by these bypass engines. As we have written down before, they have two components. One is the hot component, which produces thrust by creating hot jet. So, you have the inner flow that is going inside the hot gas generating unit, and then that producing the hot thrust. This is the inner flow that is going in. This is the mass flow of the fuel that is being pumped into the combustion chamber, and this is the hot jet velocity that is being produced. The second part of the thrust production is the bypass mass, which produces a bypass jet, which we may call V E bypass. Now, that has to be more than the V A with which the flow is going into the big fan, and this difference produces the momentum change. Now, in this second component, the more important aspect of the thrust production is not the difference between the two velocities, but the huge amount of mass that is being activated. So, in the second thrust producing component here, the mass of air that is being activated through bypass system or a bypass cold jet is indeed very high, and that is what produces a very high cold thrust from the second component. Whereas, in the first component, as we know, it is the V E hot which is the most important aspect of thrust production, because the mass flow there being processed is not of very high order. The SFC of such an engine is simply referred to in terms of the mass flow that is pumped into the combustion chamber divided by the total thrust that is being produced, the combination of hot thrust and the cold thrust, and that total together gives you the SFC. And now, one can realize, looking at this figure, why there is a huge SFC benefit when you use bypass engine, and we will of course be talking about this more and more, of this benefit of SFC of bypass engines. The overall efficiency of bypass jet engine can again be written down in terms of eta E, and as we know, this is a combination of propulsive efficiency and the energy efficiency, as we have done before, where the exhaust jet energy is now has two components. One is the hot component and one is the cold component. Now, as you can see here, the cold component has very high mass flow, but very low jet energy. The hot component has very low mass flow, but very high jet energy of its own. So, the energy waste of per unit mass flow for the cold component is going to be very low. So, per unit mass flow cold component jet waste is of a very low order, and that is one of the reasons one can conceptually understand why a bypass engine would have higher propulsive efficiency. We can take a look at this simply mathematically. Propulsive efficiency has been defined before simply by 2 divided by 1 plus V E by V A. Now, here we can write V E as V E average of the hot and cold, which we can write down here as a mass averaging, and if you do that, the V E average will be substantially lower than that of V E hot, and as a result of which this propulsive efficiency is now going to be of a very high order compared to any other kind of jet engine. It will be approaching that of the propeller or turboprop propulsive efficiency or propeller efficiency, and this is the huge benefit that the bypass engines or the turbofan engines bring to the operation of aircraft jet engines. So, we can now write down this bypass in terms of a well accepted bypass ratio parameter, which is used in every book and referred to by bypass engine specifications. This is simply the bypass mass divided by the core flow that is going into the basic engine. So, the cold flow divided by the hot flow simply is the ratio of these two is the bypass ratio, and this is simply referred to as bypass ratio in all turbofan specifications and engine specifications. We have been talking about various kinds of turbofan engine. We mentioned 3 spool engine, 2 spool engine, and somewhere out there we also mentioned that not everybody is comfortable with the 3 spool variant for very high bypass turbofan engines. The Americans, especially the American manufacturers, the General Electric company and the Pratt & Whitney company, they over the years prefer to use what is called a geared turbofan engine. Instead of going 3 spool, they prefer to use a geared turbofan engine instead of a 3 spool variant. Let us take a look at this geared turbofan engine, which is basically a turbofan engine, a bypass engine, a high bypass engine, but uses a different kind of mechanism. Let us take a look at that. You see, just like a propeller, there is a huge gearbox that is placed over here. Now, this gearbox is run by this intermediate speed LPT. This is a LPT, a low pressure turbine, as before. Now, this is powering this inner shaft, which is bringing out the power from the LPT, and on this shaft is also mounted a LP compressor, which produces a certain amount of pressurization when it is fed into the main core compressor. So, that is a bit of a booster compressor, and then this power shaft goes and mates with a reducing gearbox, and then this gearbox then produces a very low speed shaft power onto this low speed fan. Now, low speed fan is very similar to, let us say, a propeller, not as low speed as a propeller. Propellers, as I mentioned, runs at 1000, 1200, 1500 rpm. This low speed fan may be running at 2000, 2500 to 3000 rpm maximum. However, that kind of a speed is very unbeneficial or not very profitable for turbines to run. If a turbine runs at as low speed as 3000 rpm, its power producing capacity will be very low. For a turbine to produce a substantial amount of power by itself, it should run at a high rpm. We have seen in case of turboshaft engine just a while before that it runs at very high rpm of the order of 20, 30, 40,000 rpm, and then runs the rotor through a reducing gearbox. Now, the idea that turbine produces more power or more power efficiently if it runs at high rpm is a very well known phenomenon. It is very well known in gas turbine industry, and as a result most gas turbine designers would like to run the turbine at a rather high rpm. So, this intermediate speed LPT actually runs at a rather high rpm, may not be as high as the HP turbine, but still reasonably high of the order of 7 to 8000 rpm. And if it runs at that kind of a rpm, it can produce sufficient power with the help of certain number of turbines. If it has to run at a lower rpm like 3000, it would actually probably need a large number of turbines, many more. Instead, what you see here is 4 turbines. It may need 6, 7, 8 turbines to produce the same amount of power, in which case the weight of the engine would go up tremendously. So, reduce the weight of the size of and the size of the engine, this turbine needs to be run at a high rpm. If it is to be run at a high rpm, you cannot run the fan at that high rpm, and hence the gearbox. So, you can do with a gearbox in between to reduce the speed and run the low speed fan, producing a very high bypass and a very high cold thrust, but still leave the turbine to run at a reasonably high rpm with a reasonable number of sets of stages of turbines to produce all the power that is required to run the big fan. So, this is a mechanical combination which many of the big turbofan designers have adopted. that they have a gear turbofan, and this gear turbofan allows them to go very high bypass, and as a result of which all the benefits of a very high bypass can be obtained by producing this kind of engine. You need a gearbox now very similar to turboprops or turboshafts to run the turbofan. So, now we have gearboxes inside turbofans, not only inside turboprops or turboshafts, but also inside the turbofan engines, the modern turbofan engines. This is a 2-spool 3-drive turbofan engine. Now, as you can see here, you have 2 spools, one spool that is the outer spool, which is run by one set of turbines, and it runs the LP compressor. The inner set of compressors are run by the inner set of turbines, which is what we call the gas generator. And then this hot flow, it flows through a third set of turbines over here before it goes out as a hot jet and producing thrust. This third set of turbines over here actually has a big fan mounted right on top of it or right around it circumferentially. So, it directly sends power from the inner turbine blades to the outer fan blades, big fan blades, and which actually activates a very large amount of air, cold air mass flow, and produces the large bypass flow. Now, this bypass flow of course produces the cold bypass thrust. So, we have a hot inner thrust and a cold outer thrust producing cold air, and this combination goes out producing very large amount of thrust. Now, this is often called an aft fan, because the fan is not in front of the engine, but somewhat towards the rear of the engine, and the peculiarity or the ingeniousness of this particular design is that it does not have a shaft to convey the power from turbine to the fan, but the power is directly conveyed from the blades of the turbines to the blades of the fans, which rotate together on the same inner shaft. So, that is a third shaft here, which does not convey power, but it simply runs the combination of turbine and fan together on that shaft. So, it is basically a 3-drive, one may call it 3-spool if one wants to, and it is a kind of aft fan, which means the fan is somewhat towards the rear of the engine. Let us take a quick look at the bypass ratio benefits that normally comes. You can see here the graph of specific thrust versus bypass ratio. As the bypass ratio increases, the specific thrust comes down, which means the thrust produced per unit mass flow is coming down. This is pretty much well known, that if you increase bypass ratio, your specific thrust production is actually going to go down. So, when you desperately need specific thrust or thrust, you go for low bypass engine, and that is what is used in military aircraft. But when you need thrust, very high thrust at very high efficiency, you go for high bypass, in which case specific thrust, that is thrust per unit mass flow, is not very high. So, the lower end of the bypass is basically a thrust producing engine, whereas the higher end of the bypass is a very high efficiency thrust producing engine. So, the two ends are used for two different purposes, one for military purposes, the other for commercial economic purposes. And that economy is shown on the right hand diagram here. The SFC is continuously falling with the bypass. There is a dotted line here, which shows that over a period of years of usage, the thrust actually reduces slightly with overs of usage, whereas the SFC actually may slightly improve with over years of usage. It of course falls with the bypass ratio. So, at very high bypass, you actually have very low SFC of turbofan engines. This translates to most prominently in the propulsive efficiency, where the increase of bypass ratio simply increases the propulsive efficiency to very high values. As you can see here, with years of usage, it may slightly deteriorate, but it still produces very good propulsive efficiency competitive with any other kind of jet engine that one can think of. And this is the reason why turbofan engines are used in all commercial jet aircraft today, because it produces very high propulsive efficiency. And this is the kind of engine that we would probably like to look at more and more. I will leave you today with one more engine, which actually is called prop fan engine. This is a very high bypass BPR or bypass ratio of the order of 20, and this has huge big fans. Comparatively, you can see the fan size is much bigger than the basic jet engine, which could be a 2-spool basic jet engine, and this produces a third spool which comes out. It may run through a gearbox, because you may like to run the fans at a somewhat lower RPM. And one more variant is that the second fan over here, you may have 2 fans running one after another, similar to the 2 compressors running one after another. And if you have 2 fans, it is entirely possible, and it has been demonstrated that through the gearbox you can run the second fan in opposite direction, that is a counter rotation, and if you do that, you get a huge benefit in terms of thrust production and in terms of SFC. So, this is a kind of very high bypass ratio prop fan. The fans are so big, they are almost approaching the size of propeller, but not quite, and quite often even today they are ducted with this kind of ducting, because this ducting actually allows certain amount of noise suppression, and hence even today people would like to use ducts essentially to suppress the noise that is created by these big fans or prop fans, and hence the noise is kept under certain amount of regulatory control. So, this is a kind of big prop fan, an extension of turbofan with very high bypass ratio. Some people call them ultra high bypass ratio turbofans or prop fans. So, this is the kind of engines that we are likely to see more and more in years to come. So, those are the kind of various engines that we have looked at today. The various kinds of turbofan engines, the bypass ratio is going higher and higher and higher, making them more and more fuel efficient. Noise is being taken care of by various designs, and if we do that, we have more and more efficient engines coming up in the years to come to power the aircraft flight. In the next class onwards, there will be coverage of the basic aerothermodynamics of this flow through these jet engines that we have been talking about. Through the cycle analysis, this will be covered by Professor Pradeep over the next few lectures. So, in the next few lectures, you will be doing the aerothermodynamic analysis or the cycle analysis of all the engines that we have covered in the last few lectures.